Hello, everybody. How are you doing? Today we are going to be talking about rational functions and their graphs. So the first thing we're going to be talking about is what the definition of a rational function is. Then we're going to be talking about asymptotes. And we're going to see that up to now we've not been dealing with this concept called an asymptote, but starting with rational functions and going forward with exponential functions, we're going to be dealing with a concept called asymptotes. Then we're going to talk about how to find the domain of a rational function. And then we're going to talk about how to find the vertical asymptotes or holes, and then horizontal asymptotes. And then we're going to conclude with doing example types. So in mathematics, the word rational is a synonym for fraction. So whenever you see the word rational in math, think fractions. Okay. So for example, a rational number is basically a fraction, or any number that can be written as a fraction. So remember from our previous discussion, like 7/8 is a rational number, -4/5 is a rational number, -3 is a rational number because it can be written as a fraction by putting it over 1. My decimals that end, like 0.25 is a rational number because it can be written as a fraction. And repeating decimals like 0.3 bar can be written as a fraction, so they too are rational numbers. So take home point, when you see the word rational, think of the word function. Now, when you see rational, think of the word fraction, not function. I apologize. So now, a rational function is a function that is a fraction. So any function that can be written as a fraction can be considered a rational function. So up to now, we've been dealing with functions that are polynomials in nature. So for example, let's talk about, say, x squared plus 3x plus 2. So we talked about how to graph it, how to find the end behavior, how to find the zeros, etc. But if we drew a Venn diagram, rational polynomials is a specific type of rational function. So these are my polynomials. So in this diagram, these will be my equations that are polynomials. And this will be my category of rational functions. So polynomial is a type of rational function. So remember that analogy that I gave about in class about the Equus, and Equus being a type of Hyundai basically car. Well, in the same vein, remember we talked about polynomials are a type of number. So whatever you can do to a number, you can do to a polynomial. So remember in our previous example, I said -3, even though it's an integer, it's also a rational number because we can put it over 1. Okay. Well, the same thing can be said about a polynomial function. We can put the entire polynomial function over 1, and now it becomes a rational function. Okay. So a rational function is any function that can be written as a fraction. Now, polynomials are a subcategory of rational functions, and we've talked extensively about their characteristics that are unique to polynomials. So just because it's true to polynomials doesn't mean everything is true to rational functions. Key characteristic of a polynomial is that the domain is all real numbers. So for example, in a polynomial function, the domain we said was from -infinity to infinity using interval notation. But this is not necessarily the case, as we're going to find out, with all rational functions. With all rational functions, the domain is not necessarily all real numbers, and we have inconsistencies throughout the graph of that function. And we're going to get into that in a minute in our discussion with rational functions. So take home point, a rational function is any function that can be written as a fraction. So as you see with this slide, a rational function are quotients of polynomial functions. That means they can be written as a fraction p over x over q over x, where p of x and q of x are both polynomial in nature. So both p of x and q of x are polynomial. So the rational function f of x is p of x over q of x. Okay. Now, the domain of a rational function changes depending upon my value of q over x. So in general, when we were talking about, say, the rational function, which is a polynomial function, x squared plus 3x plus 2 over 1. In this scenario, p of x is x squared plus 3x plus 2, and q of x is a constant 1. And because the function q of x is a constant, we say that the domain is all real numbers. But things change when q of x becomes something else. And we're going to get into that in a few minutes. But before we get into that, I want to talk about what is the concept of an asymptote. An asymptote is a line, either vertical or horizontal, that the graph approaches but never exactly touches or crosses, specifically when we talk about vertical asymptotes. So let's take, for example, the reciprocal function f of x equals 1 over x. So this function right here, okay? Now, if I plug in -1 for x, right, f of x becomes -1 over -1, which is -1. If I plug in -1/2 for x, that means we'll get 1 over -1/2, which becomes -2. And if I plug in -1/10, which is 0.1, I get -10. If I plug in -1/100th, which is 0.01, I get -1/100. Now notice something. What is happening to my f of x as my x is getting closer and closer to 0? Because as you guys see, -1 is smaller than smaller than -0.5, which is smaller than -0.1, which is smaller than -0.01. So these numbers are approaching 0 from the left. So what is happening to my output, my f of x, as my x is getting closer and closer to 0 from the left? Yeah, my f of x is approaching infinity. Well, in this case, -infinity. So as you see from this graph right here, as my x is getting closer and closer to 0, my f of x, my output, is going more towards -infinity. Now, let's approach 0 from the right. So we're going to do the same thing. So we're going to start off by plugging in 1 for x, and then we're going to plug in 0.5, which is 1/2, 0.1, which is 1/10, 0.01, which is 1/100th, and 0.001, which is 0.1/1000th. So this is approaching 0 from the right. So if I plug in 1 for x, what do I get from my output? Yeah, I get 1. Okay. If I plug in 1/2 for x, I get 2. If I plug in 1/10th, I get 10. If I plug in 1/100th, I get 100. If I plug in 1/1000th, I get 1000. So notice, as my x gets closer and closer to 0 from the right, where is f of x going? F of x is going closer and closer to infinity. And this graph shows that as x approaches 0 from the right, f of x is going to infinity. So this begs the question, can f of x ever be 0? Can I plug in anything for x that gives me 0 as my output. Think about that. Is there anything I can plug in for x that makes my output 0? And the answer is no. The answer is no, because what happens when x is 0? Well, remember, when 0 is in the denominator, this is undefined. Remember, we can't have 0 in the denominator. So x can never be 0, but x can approach 0. But there's a problem with that. And you can see that depending on which way I'm approaching 0 on my coordinate plane, my value for f of x is going in two different directions. So as x is approaching 0 from the left, as it is in the upper diagram, f of x, my output, is getting more and more larger negative, or more and more negative, so negative infinity. As x approaches 0 from the right, f of x is getting larger and larger, more and more positive, so positive infinity. Well, what happens? So which way is it? Which one is the correct way of doing it? Well, to be honest with you, they're both correct. Okay, they're both correct. And this is what we call a vertical asymptote. A vertical asymptote is defined as as x approaches any number from left or right, f of x either goes to infinity or negative infinity. Let me repeat that. A vertical asymptote occurs when, as x approaches a number from the left or right, so as your input approaches a certain value from the left or right, your output, f of x, shoots off into either infinity or negative infinity. Okay, so if you look at this diagram right here, so in the first diagram right here, as x approaches a from the right, f of x shoots off into infinity. And as x approaches a from the left, f of x shoots off into infinity. So this is known as a vertical asymptote. So a vertical asymptote occurs whenever, as x approaches a certain number, f of x goes to either infinity or negative infinity. So if you want a quick shorthand of how to write this, we say a vertical asymptote, VA, occurs when, as x approaches a, f of x goes to positive or negative infinity. And notice, if you approach a from the left or right, if you approach it from the left, f of x may shoot to positive infinity, and if you approach a from the right, f of x may shoot to the opposite direction, negative infinity. Or it may be the case where, as you approach a from both the left or right, it approaches infinity, or they both approach negative infinity. That's still an asymptote. As long as you get closer and closer to a certain value, if your output shoots off to infinity or negative infinity, we call that a vertical asymptote. All right. Now, we have another type of asymptote in mathematics, and it's known as a horizontal asymptote. A horizontal asymptote. Now, let's go back to my f of x equals 1 over x example. Okay. Now, let's look at the situation where x, now instead of x approaching 0, let's have x go to infinity. Okay, so every input I put in for x, it's going to be progressively larger. Okay, so notice right here, as x goes to infinity, so as my inputs get larger, what happens to my output? Well, when x is 1, f of 1 is 1 over 1, or 1. When x is 1 over 10, when x is 10, f of x is 1 over 10. as when x is 100, f of x, my output, is 1 over 100. When x is 1000 in this function, f of x equals 1 over 1000. So notice, I'm going from 1 to 0.1, which is 1 over 10, to 0.001 to 0.0001. Okay. So what is my f of x approaching as x goes to infinity? So if you notice, x is going to infinity here, getting really, really large. So notice we're approaching a certain value, aren't we? If you notice, we're approaching 0. So as my x gets larger and larger and larger in this function, my f of x, my output, is getting closer and closer to 0. Okay. That's important. Okay. So as x is going to infinity, f of x is going to 0. Now, notice, let's go the other way. So instead of plugging in larger and larger numbers, let's plug in smaller and smaller numbers, or more and more negative numbers, if you will. So if you see the chart on the right, x is going to negative infinity. So first I'll plug in -1 for x, then I'll plug in -10, and then I'll plug in -100, and then -1000. So notice, a similar thing happens as x gets more and more negative, so goes to negative infinity, f of x is going to getting also closer to 0. So -1, which is smaller than -0.01, which is smaller than -0.001, which is smaller than -0.001. So as you see, as x is going to negative infinity, f of x is going to 0 as well. So this is different than when x was going to a certain number. When x was going to a number, my output was going to infinity or negative infinity. Here, as x is going to infinity or negative infinity, f of x is approaching the same number, which is, in this case, 0. So look at the graph right here. Let me blow it up a little bit for you. See? So as x is going to infinity, f of x is getting closer and closer and closer to 0. And as x is going to infinity on this side, f of x is getting closer and closer to 0. And again, this is known as a horizontal asymptote. So to alleviate any confusion, a vertical asymptote occurred when x was going to a certain number from left to right. So as in this case, in the previous example, as x approached 0, f of x shot off to infinity or negative infinity. That's a vertical asymptote. But in a horizontal asymptote, as x goes to positive or negative infinity, f of x, the output, is approaching a number. Okay. Now, does it ever get to that number? Well, that depends on the function. Okay. So again, is there anything that I can plug in for x to give me 0? No, there is no number. So it will never get to 0. My output will never get to 0, but it can get really, really close. Okay. So take home point. If x goes to infinity or negative infinity and f of x, your output, is approaching a number, that's a horizontal asymptote. Okay. So as x goes to infinity or negative infinity, f of x, your output, approaches a number, in this case 0, that is known as a horizontal. But as x gets closer to a number and f of x goes to infinity or negative infinity, that is known as a vertical asymptote. So take home point, a vertical asymptote occurs when your input approaches a number and your output shoots off to infinity or negative infinity. And horizontal asymptote occurs when x goes to infinity or negative infinity and f of x approaches a number. Okay. Now, that is not the only difference between a horizontal and vertical asymptote. The other difference is a vertical asymptote is like a wall. A graph can never cross a vertical asymptote. It is an absolute value of, you cannot pass a vertical asymptote. So the graph will never be able to cross that vertical asymptote. It'll get very, very close, but it will never cross. But a horizontal asymptote can potentially be crossed at a point. Okay. So take home points. As your input x approaches a number and f of x shoots off to infinity or negative infinity, that is known as a vertical asymptote. However, as x shoots off to infinity or negative infinity, f of x approaches a value, that is known as a horizontal asymptote. Okay. Also, vertical asymptotes can never be crossed or touched. Horizontal asymptotes can potentially be crossed at a point. Okay. Now, let's go back and talk about the domain of a polynomial function. The domain of a polynomial function, of a rational function, sorry. So, remember, in a polynomial function, a function whose denominator was 1, the domain was all real numbers. However, in a rational function whose denominator is not 1, there's a problem. And that problem is, as you can probably guess, the denominator can't be 0. Okay, the denominator can't be 0. Well, if the denominator in the case of a polynomial function is a constant, then you have nothing to worry about. So in this situation, a polynomial function, it's a rational function whose denominator is 1. The denominator, there's no value of x that makes the denominator 0. Okay. And you could try it. You could plug in different values, but there's nothing that you can plug in for x that makes the denominator 0. So you're good. So the domain for all polynomials is all real numbers. But this is not necessarily the case when you're talking about other rational functions. So let's take, for example, problem A. X squared minus 9 over x minus 3. Okay. So when we talk about domains, and remember our discussion about domains, our key point was to say, what can x not be? Remember, domain is the collection of your inputs, the collection of your x's. So when you're determining your domain, you want to know what x cannot be. In the case of polynomials, as we talked about, x can be anything, so the domain's all real numbers. However, in example A, I don't have that luxury because the denominator is x minus 3. Well, if the denominator is x minus 3, that means if x is 3, the denominator becomes 0. If x is 3, the denominator becomes 0. Does everyone see that? So if I plug in 3 for x, I get 0 in my denominator. And I can't have a 0 in the denominator, and we've talked about this. So that means the domain of f of x in example A is all real numbers except 3. So remember, this is how we write using set notation. Okay. So just to go over it, this stands for, x such that x is in R, so is any real number, and x does not equal 3. So remember, this is set notation. Now, writing the domain with interval notation means we write it like this: negative infinity to 3, union 3 to infinity. recall, why did we put a parentheses and not brackets? Yeah, because remember, parentheses means you can get close to 3, but you cannot be 3. And we can't be 3 because it makes the denominator 0. Okay. So to find the domain of a rational function, you set the denominator equal to 0 and solve. Okay, that may involve one-step equation solving, or it may be, you may have to factor, you may even have to use the quadratic formula if it's not a factorable quadratic. Okay, so take home point, the domain of a rational number, step 1, set the denominator, the polynomial in the denominator equal to 0, solve for x. And then once you solve for x, the domain would be all those values that you get for x, okay? So the domain will be all real numbers except the values that you get for x. And you can either write that using set notation or interval notation, right? Now, what x can't be is known as a discontinuity. What x cannot be is, we call that a discontinuity. So, for example, in problem A, x equals 3 is my discontinuity. And it's called a discontinuity is because that's where the graph does not exist or is discontinuous, right? And we're going to talk about discontinuities more in a couple of seconds. But before we do that, let's do some more practice problems, okay? So, problem B, find the domain for g of x. I recommend you pause the video and try to work on it yourself and then come back to see the solution. All right, so remember, the first thing we're going to do is set the denominator equal to 0. Now, how are we going to solve this? Well, remember, this is a difference of squared. First term squared minus the second term squared. So how do we factor a difference of square? The square root of the first minus the square root of the second times the square root of the first plus the square root of the second. Okay. So x equals 3, x equals -3 when we set each one of these binomials equal to 0 and solve. So that means x can neither be 3 or -3. So that means my discontinuities are 3 and -3. That means my domain is x is all real numbers and x does not equal plus or minus 3. Okay. Now, using interval notation, this is what I'd get. So x can be anything from -infinity to -3, or -3 to 3, or 3 to infinity. And since it can't be either -3 or 3, but it can get really close to it, we'd use parentheses instead of brackets. And on the test, either one is fine by me. All right, now let's do problem C. Okay, problem C. Again, pause the video and try to work it yourself and come back for the solution. All right. So step 1, we set the denominator equal to 0. Okay. And we try to solve. Well, there's a thing here. There's a problem. X squared plus 9 is not a factorable quadratic. okay? It's not a factorable quadratic. Now, you can use the square root property by moving 9 to the opposite side and get x squared equals negative 9. And as you remember, you can't square something and get a negative number. You can, but you get an imaginary solution. So we're only dealing with real numbers. So since the solutions are imaginary, there is no discontinuities. So there would be no discontinuities here. So what does that mean the domain is? Well, the domain is then all real numbers. Okay. All right. So I'm not going to walk through the problems in checkpoint 1, but I highly recommend you pause the video and try to solve them. And I'm just going to write the answers for you. And I'm going to use interval notation. Okay. Did everyone get that? Right. Now, we're going to talk about types of discontinuities. Okay, types of discontinuities next. But before we do that, let's talk about notation. Okay. And I've been using this, but I've not really explained it. If you see a plus above a number like an exponent, that plus means x approaching a number from the right. Okay. So if you take a coordinate plane, if I'm saying if this is a, x approaching a from the a plus means that we're coming from the right. Okay. Likewise, the minus means is coming from the left. That we're approaching that same number, but instead of coming from the right, we're coming from the left. And this means x going to infinity. That means going to the right. And we've talked about this in our end behavior discussion. We talked about this notation. X going to infinity means the right of the to the right of the y-axis, and x going to negative infinity means to the left of the y-axis. So this region is the right side is known as x going to infinity, and the left side is known as x going to negative infinity. Okay, so let's keep going with our discussion pertaining to discontinuities. Okay, now let's look at this rational function here. So step 1, let's find the domain, okay? So first we want to find the discontinuities. So we're going to set the denominator equal to 0 and solve. Now, how do we solve this? Well, this is a quadratic and we should try factoring first. So can you think of two numbers that multiply to give me negative 35, but combine to give me negative 2? Yeah, negative 7 and 5. So if we set each one equal to 0, we get x equals 7 and x equals negative 5. So that means my discontinuities for this polynomial, or for this, rational function is negative 5 and 7. That means my domain is x can be negative infinity to negative 5, or negative 5 to positive 7, or 7 to infinity, and so on. And it can't be negative 5 or 7. That's why we use parentheses and not brackets. But this is not where the story ends, because discontinuities come in two flavors, if you will. So there are two types of discontinuities. There's either removable discontinuities or there are vertical asymptotes. So remember about our discussion with vertical asymptotes. Vertical asymptotes are a full stop, and they cannot be crossed. Okay, they can be approached but cannot be crossed. Remember, vertical asymptotes means that as x approaches a number from the left to right, f of x, your output goes to either infinity or negative infinity. So all my discontinuities, so in this case right here, all my discontinuities are either going to be removable or they're going to be vertical asymptotes. So what are they? Well, another name for a removable discontinuity is also known as a hole. A hole. And it's called a hole because it is literally a hole in the graph. It is a point where that cannot exist on that graph. Remember, a graph is a set of all points that are solutions to that equation. And a hole is a part of the graph that just doesn't exist. A point on the graph that doesn't exist. So how do I determine whether the discontinuity is a hole versus a vertical asymptote? Well, I look at my original polynomial, my original rational function, okay? And I notice that if I factor, because I already factored to find my discontinuities, if I factor both the numerator and denominator, in which case, in this case, I just have to factor my denominator because my numerator is already a binomial, or factored, if you will, I get this right here. And I notice that the x plus 5 in the denominator and the x plus 5 in the numerator, they're considered a number, right? So they can be eliminated. Like you would, if you had a 3 in both the numerator and denominator, you can cancel those out, okay? So it's the same thing here, right? So just remember, when you have a regular fraction like 6/8, you can reduce that fraction by saying, okay, what factor does 6 and 8 have in common? And we can say, well, 6 is 2 times 3, and 8 is 2 times 4. Since they both have a common factor of 2, I can reduce this fraction to 3/4. In the same way, remember, because polynomials are numbers, I can reduce a rational function like I can reduce a rational number. I have x plus 5 in the numerator, and I have x plus 5 in the denominator, and I can remove that, okay? And that gives me a reduced rational function of 1 over x minus 7. Okay, so since x plus 5 can be removed, that means negative 5, what x plus 5 equals 0 is equals, negative 5 becomes a removable discontinuity because I can factor out x plus 5. Okay, so negative 5 is a discontinuity, and since is a removable discontinuity, it's a hole. That means that goes to that collection of discontinuities. And that means 7 must be a vertical asymptote. Okay, vertical asymptote. So how are we going to do these going forward? Well, first, you're going to find the discontinuities. Okay. Find the domain. Okay. Then we're going to factor both the numerator and denominator. Now, in this situation, maybe just the numerator needs to be factored. Maybe just the denominator needs to be factored. Maybe both need to be factored, but factor both the numerator and denominator. And then the values that cancel out, or the binomials that cancel out, those values of x are your wholes or removable discontinuity. Okay. The discontinuities that are left are your vertical asymptotes. Okay. Now, in this situation, you can have multiple things here. You may have a situation where if you have a collection of discontinuities, they're all wholes, and that you don't have any vertical asymptotes. You may have a situation where you have a mixture of wholes and vertical asymptotes. Or you may have a situation where all of the discontinuities are vertical asymptotes. So don't panic when you're doing a problem and identifying which are wholes versus which are vertical asymptotes if you have a situation where all of them are canceled out. That means they're all wholes, or they're all vertical asymptotes because none of the binomials cancel out. Okay. So this is basically the flow of how we're going to do it. We're going to first find the discontinuities. Okay. Then we're going to write our domain. Then we're going to factor both the numerator and denominator, which, to find the discontinuities, you have to factor the denominator anyways. So you may potentially also have to factor the numerator. And then we see which ones cancel out. And the ones that cancel, those values of x are known as wholes. And whatever discontinuities are left after we identify which ones are the wholes, or which values of x are wholes, whatever's left is a vertical asymptote. And this is going to make sense to you as we do a couple of problems. Okay, so let's look at this problem right here. And let's go through the steps. So the first thing we're going to do is we're going to find the discontinuities. So to find the discontinuities, we're going to set the denominator, the polynomial in the denominator, in which case is a linear polynomial. We're going to set it equal to 0, and we're going to solve. And so that means my discontinuity in this case is just one discontinuity, which is 2. Okay, now we're going to find the domain. Well, the domain is all real numbers except the discontinuities. So in this case, in interval notation, this would be negative infinity to 2, union 2 to infinity. Okay. Now, we're going to classify. Okay, so the first thing we're going to do is we're going to factor both the numerator and denominator. Now notice the denominator is already a binomial and we don't need to factor. There's nothing to factor here. But the numerator can be factored. So how do we factor x squared minus 4? So pause it and pause the video and try to factor it yourself. All right, now remember, x squared minus 4 is an example of a difference of squares. So the way we factor it is x minus 2 times x plus 2. And in the denominator, we still have just my x minus 2. So are there any binomials that can be canceled? Well, yes, x minus 2 can be canceled. Okay. That means the discontinuity, which is 2, that's associated with x minus 2, that means the discontinuity is a whole or removable discontinuity. So my whole is x equals 2. And, well, what does that mean for my vertical asymptotes? Well, that means I don't have no vertical asymptotes, okay? And you can, because we don't have any more discontinuities to classify. Now, how does this look on a graph? Well, the polynomial, the rational function x squared minus 4 over x minus 2 is just the polynomial x plus 2, which is the graph of a line, okay? The graph of a line whose y-intercept is at 2 and whose slope is 1. But notice it is a removable discontinuity. It is a hole at x equals 2. So when x is 2, we have a hole right here. So you see how we graph it. We graph the line, and then when x equals 2, wherever that line is at 2, we put a hole. Okay, and so literally it is known as a hole because that's what it is on the graph. It's a hole in the graph. The graph does not exist there. Okay, it's discontinuous out there, and it's a removable because we removed that. Okay, now let's look at A and B. Okay, so in A, let's go down and let's find my discontinuities. And for time's sake, I'm just going to quickly write out my discontinuities of being x equals plus or minus 1, okay? And that means my domain is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity, okay? So I have two discontinuities to classify, if you will, okay? Two discontinuities to classify, and that's 1 and negative 1. So when I factor for f of x, I get f of x equals x over, because I can't factor the numerator anymore, over x plus 1 times x minus 1. Now notice, nothing cancels, okay? Nothing cancels. I can't just cancel out the x. I have to cancel out one of these binomials in order for it to cancel. I just can't cancel out my variable. So that means none of these are removable. So none of these discontinuities are removable discontinuities or holes. That means they're all vertical asymptotes. So then what's a holes would be none. And vertical asymptotes are, so remember, vertical asymptote is a line, okay? It is a vertical line along which the graph will not touch. So it's point where as x approaches these numbers, either f of x goes to negative infinity or infinity, depending on which way you're approaching these numbers. So the vertical asymptotes are x equals negative 1 and x equals 1. Remember from our discussion of linear equations, x equals negative 1 and x equals 1 are vertical lines, the equations of vertical lines. So my vertical asymptotes are vertical lines that my graph can't cross. And because neither 1 or negative 1 is a hole, they're both vertical asymptotes. All right, let's have you guys do B. Now, I'm going to walk through the problem, but I highly recommend that you pause the lecture and try to do it yourself, and then come back and see how we worked it out. Okay. So in g of x, the discontinuities still are the same. It's plus or minus 1, okay? Because when I set x squared minus 1 equals to 0, I get x equals 1 and negative 1, okay? So that means my domain is still the same. Okay. Now, in g of x, while I don't have to factor the numerator any, when I factor the denominator, I get x minus 1, x plus 1. But does everyone see the difference between this and this? Okay. And in the first one, nothing can cancel. None of my binomials were able to be canceled out. However, in g of x, I have x minus 1 binomial in the numerator and in the denominator. So I can remove that. That means my holes are x minus 1 equals 0 or 1. So 1, positive 1 is a hole, okay? And my vertical asymptote is what's left, which is x equals negative 1, okay? Because once I cancel out x minus 1 from both the numerator and denominator, all I have left is x plus 1, which means negative. That's where I got my negative 1 for x. That is my vertical asymptote. So take home point. Determine your discontinuities by setting the denominator equal to 0, factor, and solve. Okay, so those are when you calculate the discontinuities or determine the discontinuities, those are the values that the domain cannot be. Those are the values of x that x cannot be for this rational function. So then write out your domain, okay, using either set notation or interval notation. Then go back. Now we're going to have to classify these discontinuities as either wholes or vertical asymptotes. And so in order to do that, we're going to factor the numerator when possible and factor the denominator when possible. And then we're going to look for binomials or things that can cancel, okay? So like in the first case, nothing cancels, so I have no wholes, and they're all vertical asymptotes. But in the second case, x minus 1 was able to be canceled or removed. So x minus 1 means x equals 1. So the whole is at positive 1, and the vertical asymptote is at negative 1. Okay, well, let's have you guys do C. I recommend that you pause the video and come back and to see the solution. Now, I'm not going to walk through it, but there's no discontinuities. That means my domain is all real numbers. And that means since I have no discontinuities, I have no wholes. And I have no vertical asymptotes. So, question. Why don't I have any discontinuities? And if you said x squared plus 1 can't be factored, that's why. Good. All right, now the next thing we're going to be talking about is the next type of asymptote that I alluded to earlier in this lecture, which is a horizontal asymptote. Right, so our horizontal asymptotes are, okay, so remember vertical asymptotes is as x approaches a value, f of x, or your output shoots off into infinity or negative infinity. It's a vertical line that the graph cannot cross or even touch. Horizontal asymptote is the reverse. As x goes to infinity, infinity or negative infinity, f of x approaches a certain number, okay? That is known as a horizontal asymptote, and it may potentially be crossed. So, sometimes it's easy to determine what the horizontal asymptote is. So in our previous example, when we talked about horizontal asymptotes, we talked about the reciprocal function or the function 1 over x, which is known as a reciprocal function. Well, as you can tell, as x gets larger and larger, either in the positive or negative, f of x approaches 0, okay? So that means the horizontal asymptote is at 0, at y equals 0, okay? But sometimes finding the horizontal asymptote is not that obvious, okay? So there's a little shortcut that we use, and this is it. And the horizontal asymptote is determined by the degree of the numerator, polynomial in the numerator versus the degree of the polynomial in the denominator, okay? Remember, the degree of a polynomial is its largest exponent, okay? So let's talk about what it says. Given a polynomial in the numerator, a to the n and x to the n plus so on and so forth, over a polynomial in the denominator, b of m, x to the m, so on. If the polynomial in the numerator, if the polynomial in the denominator has a larger degree, if the degree in the denominator is larger than the degree in the numerator, okay, the degree in the denominator so if the degree of the if the degree of the if the degree of the denominator is larger, much larger than the degree of the numerator, the degree of the denominator is larger than the degree of the numerator, or another way of saying if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote occurs at y equals 0, or your x-axis. So if the polynomial in the denominator is greater than the degree of the polynomial in the numerator, then the x-axis, y equals 0, is your horizontal asymptote. If the degrees are the same, then the horizontal asymptote is the ratio of the leading coefficients, and we're going to get to that in a second. And if the degree in the numerator is larger, then you don't have a horizontal asymptote. So one says if the degree in the denominator is larger, then the x-axis, or y equals 0, is your horizontal. If the degrees are the same, then it's the ratio of the leading coefficients. And number 3 says that if the numerator is greater, you don't have a horizontal asymptote. So let's see how we're going to do this. So let's look at example A, 4x over 2x squared plus 1. Well, if we look, the degree of the polynomial in the numerator is 1, and the degree of the polynomial in the denominator is 2. So since the degree of the numerator is smaller than the degree of the denominator, so since the degree of the denominator is larger, see, notice the degree in the numerator is smaller, degree is larger. That means my x-axis, or y equals 0, is my horizontal asymptote. Does everyone see that? You may want to pause and re-listen to that. Because the degree in the denominator is larger than the degree in the numerator, that means it is my x-axis, whose equation is y equals 0, is my horizontal asymptote. Now, B, notice both the degree in the numerator and the degree in the denominator are 2. Okay, so both have a degree of 2. So now that means my horizontal asymptote is the ratio of the leading coefficients. Remember, the leading coefficient is the number in front of the variable with the largest exponent. So the leading coefficient of the numerator is 4, and the leading coefficient of the denominator is 2, which reduces to 2. So my horizontal asymptote is y equals 2. Now, C, the polynomial in the numerator has degree 3. And the polynomial in the denominator has a degree 2. Well, what does that mean? Well, since the numerator is larger, because the numerator is larger, there is no horizontal asymptote. Okay. So let's go over this one more time, because I know this is confusing. In example A, the degree of the numerator is 1, the degree of the denominator is 2. So the denominator is larger, x-axis, which has the equation y equals 0, is my horizontal asymptote. In B, degree of the numerator and denominator are both 2. Okay, so since the degrees are the same, I write y equals the ratio of the leading coefficient, so 4 over 2. So that reduces to 2. So y equals 2 is my horizontal asymptote. And in C, since the degree of the numerator is 3 and larger than the degree of the denominator, which is 2, I have no horizontal asymptote. Okay. So how does this look? Okay. So here are the graphs of this. So notice in this graph, the degree of both the numerator and denominator are the same. Okay. So it's the ratio of my leading coefficients, y equals 2. So you see the graph as x goes to infinity on the right or negative infinity on the left, f of x, the output is approaching this horizontal line, y equals 2. Okay. Now, in the next example, in the next drawing, the degree of my numerator is smaller than the degree of my denominator. So, or another way of saying that, the degree of the denominator is larger. Okay. So because the degree of the denominator is larger, then y equals 0 is my horizontal asymptote. So y equals 0 is another name for the x-axis. So as you see, the graph gets closer and closer to 0, but we'll never get there. Okay, so as x goes to infinity, f of x gets closer and closer to 0. And as x goes to negative infinity, f of x gets closer and closer to 0. Now, the last example, the degree of the numerator is larger than the degree of the denominator, so I do not have any horizontal asymptote. I have no number that the output is approaching. Right. So let's see. So first, now, notice horizontal asymptote has nothing to do with discontinuities, nothing to do with vertical asymptotes, nothing to do with holes. Horizontal asymptotes are their own thing, okay? So let's look at the stuff that we've written. So we're going to find the discontinuities, then we're going to, once we find the discontinuities by set the denominator equal to 0 and solving, we're going to write the domain. Once we write the domain, we're going to then take my discontinuities and classify them as holes versus vertical asymptotes. And in order to do that, I got to factor to see if any of the binomials or any of the values can get eliminated. If nothing gets eliminated, then all of my discontinuities are vertical asymptotes. If whatever can get removed are holes. Okay. Now, the last thing we're going to do is find any horizontal asymptotes. So that's the last thing. Once we deal with our discontinuities and we classify them, then we find the horizontal asymptotes. To find the horizontal asymptote, remember, if the degree, so if the numerator is smaller than the denominator, or if the denominator is larger, then y equals 0, the x-axis is my horizontal asymptote. If the degrees of both polynomials are the same, then it's the ratio of the leading coefficient. And if the numerator is larger or the denominator is smaller, whichever way you want to say it, then we have no horizontal asymptote. So for test purposes, you will not be asked to graph a rational function. Rather, you will be asked to state the discontinuities, state the domain, classify the discontinuities as holes or removable versus vertical asymptotes, and then state the horizontal asymptotes. Okay. So this is a good thing to write down and practice with for rational functions. Okay, now I want to do a couple of examples where we list out all these characteristics of the rational function, the ones that you're going to be required to do on the test. So this comes from the practice problems packet. It's the practice problems part 2 in your practice problem set. So let's look at number 5. Okay, we're going to list all the discontinuities, the domains, holes, vertical asymptotes, and horizontal asymptotes. Okay, so first one. So let's look at number 5. First thing we're going to do is we're going to set the denominator equal to 0 to find my discontinuities. Now, for the test, every rational function that I'm going to give you will be factorable to a certain extent, if they're factorable. Okay, I'm not going to give you any polynomial where you have to use, like, rational root theorem or the quadratic formula or anything. So at most, you're going to have to know how to factor. Okay, so let's look at this. So x squared minus 3x plus 2. Set it equal to 0. So how do we solve this? Well, we would factor this. Two numbers that multiply to give me positive 2 but add to give me negative 3. That's negative 2 and negative 1. So that means my discontinuities, if I set these binomials equal to 0, are 1 and 2. That means my domain is negative infinity to 1, union 1 to 2, union 2 to infinity. Okay. Now, we're going to factor because I want to classify these as holes versus vertical asymptotes. So I've already factored my denominator, but remember, I need to also, in this case, factor my numerator. Now, before we can factor the numerator, remember, we want to, before we factor, we want to make the leading coefficient positive. But in this case, the leading coefficient's negative. So we want to factor out a -1. So when we factor out a -1, remember, by factoring out a -1, the entire polynomials, all the signs change for all the terms. Okay. So when I factor this, what do I get? I get two numbers that multiply to give me -6, but combine to give me +2. So that is x plus 3, x minus 2. So that is the numerator factored. So f of x equals the factored numerator over the denominator, which I had already had to factor in order to find my discontinuities. Now, are any of these binomials removable or cancelable? Yes. X minus 2, they both factor out. Okay. Well, what does that mean if I can factor out x minus 2? That means my whole is 2. Okay. And since my whole is 2, the other discontinuity, which is 1, must be my vertical asymptote. Okay. Now, I have to now find my horizontal asymptote. Well, let's see. The degree of this guy is 2, and the degree of this polynomial is also 2. So remember what happens when the degrees are the same. The horizontal asymptote y equals the ratio of the leading coefficients. So the leading coefficient in my numerator is -1, because remember, it's an understood -1 here over 1, which simplifies to y equals -1. So on a test, these are the things that you're going to have to do. 1, 2, 3, 4, 5. These 5 things. All right. Okay. Any questions so far? If you have any, if you're uncertain, I'd pause and re-listen to this whole lecture or go through it a couple of times. And remember, when we meet again during our video conferencing sessions, then you can ask any questions. All right, let's do something a little bit more involved. Let's do number 9. Okay. So the first thing I'm going to do again is set my denominator equal to 0 and solve. Okay, now when I'm factoring, remember what's the first thing that I have to always do? I have to factor out any greatest common factor, in which case I do have a greatest common factor because all these numbers are divisible by -4. So I factor out a -4, I get x squared plus x minus 2. Okay. So when I factor this polynomial, I get x plus 2 times x minus 1. Two numbers that multiply to give me -2, but add to give me +1. Okay, that means my discontinuities. Remember, how do I solve this? I set everything with a variable equal to 0. So x plus 2 equals 0, x minus 1 equals 0. So if x plus 2 equals 0, that means one of my discontinuities is -2. And x minus 1 equals 0, that means the other discontinuity is 1. Right. Now, domain. Domain is all real numbers except that. So negative infinity to -2, union -2, 1, union 1, infinity. Okay, good. Now, we're going to have to classify this. Okay, so we're going to have to factor potentially our numerator and denominator. Now, in this situation, we've already factored the denominator in order for us to even find the discontinuities. So we only have to really worry about the numerator. Now, when we factor the numerator, again, we first look for any greatest common factor. Okay, and a greatest common factor may not just be a number, it may be a variable. It may be both a number and a variable. But in this case, the greatest common factor is a variable. We can factor out x from both of these terms. So factor out x, I'm left with x squared minus 16. Now, how do I factor x squared minus 16? Well, if you remember, this is a difference of squares. So this is x minus 4, x plus 4. Okay. Now, that means that my my rational function in fully factored form is x times x minus 4 times x plus 4 over -4 x plus 2 times x minus 1. Now, I want to see if any of these things can be canceled out. Well, if you notice, nothing can be canceled. So that means I have no holes. And that means all of my discontinuities classify as vertical asymptotes. So my vertical asymptotes are x equals -2 and x equals 1. Now, the last thing we want to do is horizontal asymptote. Now, horizontal asymptote, remember, we have to look at our degrees of both the numerator and denominator. This is degree 3, and the denominator's polynomial is degree 2. Now, remember what happens when the degree of the numerator is larger. Okay, remember, if the degree of the denominator is larger, then it is the x-axis, or y equals 0. If they're the same, then it's the ratio of the leading coefficients. But in this case, if the degree of the numerator is larger, like in this case, that means we don't have a horizontal asymptote. So we would say none. Because degree numerator greater than degree denominator. There we go. So I've given you quite a few practice problems that you can do and visualize. And I did also provide the answers for the practice problems, not for all of the study guides though, okay? It does give you the x-intercepts, but I'm not going to ask you to find the x-intercepts, okay? And that's the end of this lecture. I know it was a lot of information, and a lot of it is I'm asking you to remember a lot. However, if there's any source of confusion, I ask you to listen to the lecture again, and please formulate questions to ask me at our next video conferencing group session. Well, until next time, I will talk to you later. Bye.